Before I say anything, okay, perfect. We started recording. Okay, so Assalamu alaikum everyone. My name is Maryam Altayeb, and I'm a final year medical student. So I'm your senior. I'm a 5th year, finally. And today we're going to be talking about amino acids. So I'm going to give you guys 2 lectures. One is the basics, and then second is titration curve. I know these, well, basics is usually a bit easier, but the titration curve can be a bit challenging. And inshallah, we're going to, by the end of today, make sure that you at least know half of it, or at least understand the basic concept. First of all, it's so funny to me, but my shirt says it's Kermit the Frog, and it says the vibe is in shambles. And that is exactly how I felt in first year with MOL. Although like now I come to enjoy it, but at the time we were going through it. So I completely understand everything you guys are going through. And like I said, inshallah, we're gonna try to make this as easy and as smooth as possible. If you have any questions, feel free to stop me, ask in the chat, and I will periodically stop and make sure that there are no questions left unanswered and everyone understands everything. So let's start with the basics. Welcome back to Biochem. Like I said, if you have a question, just write it in the chat and we'll collect them and then I'll answer them in between. Also, second thing, with understanding now, I encourage you guys to get questions wrong, to ask questions, because this is how you learn, and it's much better for you to make mistakes now than in the exam. And I mean, it's scientifically proven that if you make a mistake, you're more likely to remember that fact. So don't be shy, and I think this is a very safe learning environment for everyone. Okay, so what we're going to talk about are these different objectives. So we're going to identify the functional groups and basic structure of amino acids, list and name the 20 common amino acids that you guys should memorize, and classify amino acids according to polarity and charge, relate their properties to function, and then understand some of their clinical significance. Now, I know this looks like a long-winded introduction, but to make it a bit more enjoyable, I want you guys to watch this video. Okay. I'm going to mute myself on my phone, though, so that you can hear it through my computer.
إيش حيقولوا عنك؟ إنك مو المفروض تكوني هنا، إنه ده مو ليكي، إنه دي ما هي لعبتك، أو يمكن يقولوا إنك قوية، إنه ما حد يقدر يوقفك، إنك حتلاقي طريقك، إنك قدهم، إنك أبهرتيهم. أو يمكن يقولوا إنك حتصيري شيء كبير.
Okay, so I'm not sponsored by Nike, although genuinely I wish I was. And this is single-handedly my favorite ad they've ever made. But the point of me was not showing you a Nike ad. The point of this is so you guys can see every intricate movement. Everything is because of proteins in the body. And proteins are made up of amino acids. And so today we're going to understand what amino acids are in the first place. I just thought that was, very fun introduction, and I do love that video. Okay, so what is an amino acid? First of all, can you guys hear me clearly, or do you want me to raise my voice more? Just let me know in the chat. Clear? Okay, wonderful. Okay, so what is an amino acid? An amino acid is a molecule that contains an alpha carbon, and we're going to talk about what that means in a second, bound to 4 things. One is a hydrogen atom, one is an amino group, one is a carboxylic acid group, and the 4th is a side chain, or what we call an R group. And I'm going to show you what that looks like in a second. But the basic thing is all of the movements, all of the processes in our bodies are capable because of proteins. And these proteins are made up of amino acids. And these amino acids are made up of an alpha carbon in the center bound to 4 different things. So again, hydrogen, amino group, carboxylic acid, and a side chain. that varies between different amino acids. So this is what it looks like visually. This is the alpha carbon. And when we say alpha carbon, it's basically based on chirality, okay? This is a carbon that has all different groups bound to it. That's why we call it the alpha carbon, or the central part. Okay, so you can see here that the alpha carbon is chiral or asymmetric. What that means is, exactly like I said, it's bound to different groups on all sides. It's not like there's a hydrogen here and a hydrogen here. It's asymmetric. They're not equal on all sides. Okay, and so again, we said there are 4 things bound to each amino acid: a hydrogen group, a carboxyl group, which is COOH, and I'm gonna need you guys to remember this, okay? So we have hydrogen, we have a carboxyl group, we have an amino group. Remember, amino means it has a nitrogen, so N bound to 2H, and an R side chain. And so every single amino acid we're gonna learn about, every single amino acid in the body, whether you make it or you eat it through protein, has all of these 3 side groups, okay? Every single one of them has a carboxyl group, every single one of them has a hydrogen, and every single one of them has an amino group. But how can we tell that an amino acid is, let's say, glycine versus leucine or lysine or whatever? Is by the side chain or the R group. So this is what makes each amino acid special or different, and this is what gives it different properties, and that's what we're going to learn about. So this is, again, the basic structure for any amino acid that you're going to encounter. And you have different forms of amino acid. Remember how I told you there's chirality, or this asymmetric carbon atom? It's kind of like your right hand and your left hand. They look like mirror images of each other if you put them in front of each other. But if you stack them on top of each other, no matter what you do, they're not going to align because they're different forms. They're arranged differently. So they look like mirror images, but if you stack them on top of each other, they are different. Okay, and so that's what we're seeing here. There's mirror images. So you have L amino acids and D amino acids. Okay, except for glycine, which we're going to talk about in a second. All amino acids in the body are in the L form. Okay, so if in a question you see something about L-lysine, L-lysine, that just means this is the form of lysine that is found in the human body. It's like saying every single lysine is arranged like your left hand. And you have other amino acids that you can find in different, environments and different species, I guess, not humans, that can be in the D form, not the L form. Okay, so I just remember L for left hand, and this is how all of the amino acids are arranged in our body. Okay, so again, they're mirror images of each other, or if anyone remembers from high school chemistry, they're called enantiomers, but we're not going to go into that now. Just remember that L amino acids are what you see in the human body. Okay, and so we said amino acids are the building blocks of proteins. They're like Legos. Okay, so all of these represent different amino acids, and when you put them together, this is what makes the almost infinite number of proteins we have in our body. Okay, and so now I kept talking about amino acids and what their structure is and how they're different. Let's actually learn about what you guys need to know. This is a long list of the 20 amino acids, okay? But what I want you guys to notice is that they usually have the suffix "ine," right? Alanine, arginine, asparagine, except the acids, aspartic acid, glutamine, cysteine, they all sound the same, okay? There's a few exceptions like tryptophan, glutamic acid, aspartic acid, but even then, all of them have this kind of similar sounding name. And you might encounter the full name like alanine, or you might find it as ALA, which is the shortened version. Scientists got lazy and were tired of writing them down every single time, so they came up with abbreviations. Okay, so alanine is ALA, arginine is ARG, asparagine is ASN. Like there are some of them that might be confusing, but again, that's what these are if you encounter them. Okay, and so now we're talking about amino acids. Now we need to know, okay, we know what they are. We know what they look like. We know that they're in the L form in the body. And we know that you can have short and cute names for them. But how do we get them in the first place? Well, there are 2 main sources. One is from your diet, Okay, so that's eating protein in any of its forms. Okay, and then your body breaks it down and then absorbs it as amino acids, so obtained from the diet. Or some of them can be synthesized in the body. So all of these annoying cycles that you guys are learning about in MOL help to replenish stores of specific amino acids, depending on the cycle. And so there's two types of amino acids, or two general categories. If you can only get them from the diet, they're essential. You need them. You need to eat this in your diet. Otherwise, your body can't create it. Makes sense, right? Other kind is synthesized in the body, and that's what we call non-essential amino acids, meaning that you don't necessarily have to eat them or obtain them externally for your body to have them. Your body uses different molecules and compounds in order to create it. Okay, so again, we have essential amino acids, which you must obtain from the diet. You can't get them anywhere else. You can't make them. And then you have your non-essential amino acids, which can be made in the body. Okay, is that clear so far? Any questions? Clear? If you guys have questions, feel free to stop me at any time. Great. So now let's talk about the essential amino acids. Honestly, what I did in first year and what has, kept me going since then in terms of MOL is I memorized the essential ones. Everything else is non-essential. And it's much easier that way. Okay. So the essential amino acids are 10. So if you memorize half of them, you know the rest are non-essential. And that can come as a potential MCQ. Okay. So a mnemonic that they always include and have included since I was in first year is private Tim Paul. Okay. So this is just a mnemonic to tell you which of the amino acids are essential. So private, P being phenylalanine, V being valine, and T being threonine. Okay, so private. And then Tim, T is for tryptophan, I is for isoleucine, and M is for methionine. Okay, and then Hall, H is for histidine, A is for arginine, L is for lysine, and the last L is for leucine. Now, the one thing that people would usually get confused about is tryptophan, threonine, and if you guys, I'll just go back and show you what the other amino acid is, tyrosine. So people would always get confused and think tyrosine is the essential, but it's not. They're threonine and tryptophan. Tyrosine is considered non-essential. Again, if you memorize this, the rest are just by default non-essential amino acids. So again, helpful mnemonic, private Tim Paul. P is for phenylalanine, V is for valine, T is for threonine, and then tryptophan. Remember, not tyrosine, threonine and tryptophan. I is for isoleucine, M is for methionine, and then Hall, H is for histidine, and then arginine, and then L is for lysine, and the last L is for leucine. I know no matter how many times I recite it back to you guys, you're not going to memorize it instantly, and that's completely okay. Just keep the mnemonic in mind. Even if you want to write it down on a paper and, the exam, it really helps. Okay, so just remember, these are your essential amino acids, meaning you must obtain them from the diet. You have to eat them, otherwise your body can't make them whatsoever. And everything else is non-essential. All right? So again, basically, the rest of the amino acids, all non-essential. These can be made by the body. That's why they're called non-essential. Okay? Now, that's one way of classifying our amino acids as essential, you need them, non-essential, you can make them. Okay? There's another way of classifying the amino acids, and those are based on ketogenic or glucogenic amino acids. So again, all of these really annoying pathways that you guys are learning about in MOL, some of them go towards the path of ketogenesis, which I think you'll learn about later if you didn't already, which is when you use the metabolism of fat and creating ketone bodies. And then you have glucogenic amino acids. Glucogenic amino acids means that you can turn them into glucose through gluconeogenesis, which is, if you want to break down the word, gluco refers to glucose, neo meaning new, and genesis to create. So making new glucose in the body, and that happens in the liver. So ketogenic amino acids are used to make ketone bodies. Okay. Glucogenic amino acids, as the name suggests, can be used to make glucose. okay? And some amino acids can go either way. They can go either the ketogenic pathway or the glucogenic pathway. And so the mnemonic for the ketogenic amino acids is KIL. So remember, K is for ketones, and these are lysine and leucine, okay? And then PIT is both. So phenylalanine, isoleucine, and here you have all three T's, tryptophan, threonine, tyrosine, okay? So again, it's so much easier if you just memorize that these are ketogenic, these are both by default. Everything else you're learning about is glucogenic, okay? So it's easier for you guys to solve these MCQs and to, retain this information, not by saying and memorizing every single detail, but memorizing and then knowing that the rest is by elimination, okay? So again, ketogenic amino acids are lysine and leucine. Both ketogenic and glucogenic amino acids are phenylalanine, isoleucine, and then the three T's, tryptophan, threonine, tyrosine. And do you guys remember of these three T's, which one is non-essential? If you don't, it's just so you guys can keep up. Great, yes, tyrosine is the non-essential one. And just to recap the slide one last time, we said amino acids can be essential. Remember the mnemonic private Tim Hall, or non-essential. Essential, you need it, you need it, you can't make it in your body. Non-essential, you can make it. Second way we can divide amino acids is ketogenic, meaning it makes ketone bodies. Glucogenic, meaning it helps make glucose, or both ketogenic and glucogenic. Remember, your ketogenic amino acids are two. KIL is the mnemonic, so ketogenic is lysine, leucine. Okay. Both ketogenic and glucogenic is PIT, phenylalanine, isoleucine, and then the three T's, tryptophan, threonine, tyrosine, and remember, tyrosine is the only non-essential amino acid that starts with a T. Okay. And okay, before we continue, any questions? Everything is clear? Accidentally. Just let me. All good, guys? I need a cue, yes, no, maybe. I'm not getting anything in the chat. Okay. So let's recap what we said. Remember how in the beginning I told you that you have this alpha carbon and it's surrounded by 4 different groups, right? Every amino acid has a carboxyl group. Every amino acid has an amino group, okay? And every amino acid has a hydrogen, and lastly, an R side chain. And remember what I said, based on this R side chain, okay, we can classify the amino acids. This is what's different for every amino acid, okay? Should we know ketogenesis for the exam? If you guys didn't take it yet, then it's going to be part of your final, not part of your midterm. So don't worry about it too much. But I remember Dr. Hanat mentioned that a lot in my slides. So don't worry for now. I just wanted to make sure that you guys understand what the difference is. Okay, so now back to this. Remember, we have these 3 groups that are always the same, and the R side chain is what makes each amino acid different than the other. So our groups can be aromatic. So if you guys remember from high school chemistry, aromatic means it has a ring in its side chain, or like a benzene ring, okay? It could contain sulfur. And you can also classify it as hydrophobic. So hydro meaning water, phobic meaning afraid of, so repellent of water, or hydrophilic. So again, hydro meaning water, philic meaning loving, so water loving. And so when we look at something hydrophilic, that's what we consider a polar compound, right? So here we can subdivide it. It can be polar but basic, okay? Polar but acidic, or polar but uncharged. Okay, so again, this is just a few examples of what the R groups can be. And specifically, the important ones I want you guys to keep in mind is the ones that contain sulfur, and you'll see why in a bit, the hydrophobic ones, and the basic acidic. these can be, you know, further subclassified. But again, I'm going to go through them in a minute. So I'm telling you about all these different R groups and all the different ways they can be, you know, unique to one another. But why do my mouse has a cursor, so I keep, you know, sliding it back. Anyway, so like I was saying, we keep learning about these R groups and they're different and all of these different things. But why? Why does it matter? Why do we need to know this? Well, it's very important for protein folding. Remember we said amino acids together, like Lego blocks, are going to make our proteins. Okay, and when you have different types of side chains, so we know that, let's say, if you have a non-polar compound, what's that going to do? It's going to be in the middle of the amino acid away from the water as much as possible. If you have something polar, it's going to be more on the outsides, right? Makes sense. It's going to be more towards the water in the human body. And so the different amino acid side chains determine how the protein folds and how it behaves. And so enzymes in our body that we learn about are proteins. And we'll learn, especially next lecture in more detail, that changes in the pH can alter the structure of a protein, right? So by, let's say, if you have very acidic pH, for example, or very high temperature, this can cause denaturation, if you guys have heard of that. Okay, so denaturation is when the protein breaks down. And it breaks down because different imbalances can cause these R groups to react and kind of, instead of it being folded, break apart and, you know, fall apart. Okay, so again, R groups determine how the protein folds. If you have something that's very hydrophobic, it tends to be in the middle where you fold over it. If you have something hydrophilic, it tends to be on the outside. Okay, tends to like water, so it stays on the outside. Okay, and why we care about this is because different changes in pH, different changes in the environment of the body can break down these protein structures. And proteins, you know, are what enzymes are made up of. Enzymes are proteins. And so when these denature in the body or break down in the body, they do not function properly. And this is what causes a lot of the diseases and things that we're going to see in medicine, especially later on, inshallah, once you guys get to second year and third year. And so second part is R groups determine the position of an amino acid in the protein. That's the same thing that I said in different ways, where let's say if it's hydrophobic, it stays in the middle, you're going to fold over it, determines the position. Okay. Is this clear to everyone? Yes. Okay, wonderful. So to answer your question, Amina, I want you to know which amino acids are acidic and which amino acids are basic. Okay? Because those are honestly the most unique ones. Knowing which ones specifically are non-polar, which ones specifically are polar are not going to help you as much. Okay, I'll raise my voice a bit. So what I was saying here is what I want you guys to remember right now is which amino acids are acidic and which amino acids are basic, okay? Because these are honestly the most unique ones and everything else is not very relevant for you to remember, okay? So remember, your acidic amino acids are A and G, so aspartic acid and glutamic acid. Makes sense. Okay. It's easy to remember because they have acid in the name. And your basics are lysine, arginine, and histidine. Okay, so these three are your basic amino acids. And histidine is one of the most important and potent buffers in the body. Okay, but again, if you just remember, if you just remember that the acidic amino acids are aspartic acid and glutamic acid, and your basic amino acids are lysine, arginine, histidine. Okay, so that's mostly what you need to know. I love that, Shahad. Okay, so Shahad is saying for the basic ones, you can remember the mnemonic. His lies are basic. His, because, you know, histidine. I like that. Very nice. Okay, And okay, so we talked about how some amino acids are acidic, basic, polar, non-polar. Okay, and remember, anything acidic or basic is automatically considered a polar amino acid. All right, so now we look at primary and secondary amino acids. Now, why are we subclassifying them? You'll see in a second. Easy to remember. All amino acids are primary except proline. Okay, why? Because proline is the only secondary amino acid. Okay, because its side chain is attached to both the amino group and the carbon. So what does this mean? Remember how? Okay, if you ignore these two parts at the bottom, we said every single amino acid has a carboxylic group here, has a hydrogen, and has an amino group, and then the R chain. So basically what they're saying here is this is the R chain, everything in pink, of proline. Okay, you have CH2, and then it binds to another CH2, and then it binds to a CH2, which binds to the nitrogen. So it kind of creates this internal ring. And proline is the only amino acid you'll ever see that has this internal type of ring structure, which is why it's considered a secondary amino acid. And okay, why do we care that it's a secondary amino acid? Because this structure allows it to contribute to the formation of collagen. Now, when I gave this lecture in pre-med in 2020, I gave them an example of, collagen is part of everything in your body. It's part of your bones, it's part of your skin, it's part of everything. And you guys are going to learn about collagen synthesis as well. So imagine if it didn't have this tough structure that allows it to have, the ring formation of what we know to be collagen, it would be very weak. So subhanAllah, the way our body is created is crazy and the best way possible. So this kind of stronger structure within proline itself allows the collagen in our body to be more structurally intact. So if this didn't exist, all of our bones would be, jello. So I just thought that was, something cool to include. So that's the first thing. Does anyone have any questions about primary and secondary? Or are we good so far? I'm gonna give you a second. All good? شكرا أمينة لأن قاعدة تتفاعلي معي وشاهدتوني. Okay. So can you repeat? Okay, perfect. I will definitely repeat. So we have another way to classify amino acids. That are primary amino acids and secondary amino acid. Okay, primary is everything. All amino acids are primary except one is secondary, and the secondary amino acid is called proline. Why do we call it a secondary amino acid, and why is that important? Do you see the side chain here that's highlighted in pink? Do you see how it's going back and attaching to the nitrogen group? This is very unique to proline. No other amino acid does this and kind of comes back and hooks into its other chain. Okay, so it doesn't have this ring structure, most amino acids, except proline. So because of this ring structure, it's considered a secondary amino acid. And this allows proline to be a part of the formation of collagen. And so collagen has many types, types 1, 2, 3, 4, okay? And they make up a lot of different structures in our body. And so this secondary structure helps the proline make collagen a stronger structure, which is, how we maintain our skin, our bones, and, a million different structures in the body. Okay, great. So now we move on to aromatic amino acids. Remember, aromatic means they have a benzene ring, which is this little thing here that's highlighted in pink. So every single one of these has a benzene ring. Okay, and so the aromatic amino acids are 3. You have phenylalanine, you have tryptophan, and you have tyrosine. Again, we're not learning about these things, although they seem redundant and boring, for no reason. So what these aromatic rings do is they absorb UV light, okay? And you'll see that because of their structure, they can be used in different ways in the body. And because they're able to absorb UV light, they can be detected by a device called a spectrophotometer. So what this does is it basically tells you that this aromatic ring is going to absorb UV light. And when it absorbs the UV light, we can detect it using this device. Okay, and it has a lot of different uses in the body. So, I'm not going to go into detail now, but, tryptophan has its specific uses, importance in depression, tyrosine, all of these different things. Okay, but again, these amino acids have aromatic rings. And why do we care about tryptophan? Okay, again, it's the same amino acid that we just talked about here. So tryptophan can form niacin, or vitamin B3, okay? And it is a precursor, or the molecule that comes before serotonin. So even not in a medical context, if you guys have heard of serotonin, it's now called, the happy hormone, okay? And it's a neurotransmitter, or a chemical in the brain that has a calming effect, okay? And sometimes, in very specific scenarios, people might have a deficiency in tryptophan. Remember, if we go back to the mnemonic, Private Tim Hall, one of the two T's, it was threonine and tryptophan. So you need to obtain tryptophan in the diet. So diets that are very poor in tryptophan can contribute to depression because your body is not able to make tryptophan, which means it's not able to make serotonin. So, depression can be managed by controlling your serotonin levels. And of course, this is not the only reason, but tryptophan deficiency can contribute to that in other ways as well. So I just thought this was just an interesting thing for you guys to know, because serotonin has a lot of buzz around it, especially in the TikTok world right now. So any questions so far? Just to recap, anything aromatic means it has this ring. These absorb UV light, these rings, so they can be detected by a device called a spectrophotometer. And we have, phenylalanine, tryptophan, tyrosine. Tryptophan is important because, first of all, it can form niacin, vitamin B3, which is important for our bodies. Okay, and it's a precursor to serotonin. And lack of serotonin is not what specifically, but one of the factors that contributes to depression. Okay. All right. So we're almost at the end of the first lecture. One more point I want to emphasize for you guys. Remember how I told you you can classify the R groups in different ways, like either hydrophobic or hydrophilic or aromatic. And the last one that was unique that I told you to remember was sulfur containing. Okay, and so methionine contains sulfur, and cysteine also contains sulfur. And why we care about sulfur, okay, is because cysteine, which I highlighted here in pink, can form disulfide bonds. So di meaning two, sulfide referring to sulfur, and bonds, okay? So you see the S here and the S here that are highlighted in yellow. So this is one cysteine molecule on this side of the amino acid, or this side of the protein chain, okay? And on the other side, there's another amino acid, another cysteine. And because there's a cysteine here and a cysteine here, the two S's, or the two sulfurs, like to stick together. So they bond together and form what we call a disulfide bridge. And you guys notice how, because of this disulfide bridge, the protein folds, it forms this new shape. Okay, so this is an important factor in stabilizing the final structure of the protein. Are we expected to know the amino acid if they give us its structure? Okay, the main amino acid that you might be asked about, to my knowledge, and don't quote me on this, because this is just historically what I've seen in Alfa-Salmon, is they like to ask about glycine. Glycine is the only amino acid that has two hydrogens attached to it. So it's the only amino acid that is non-chiral, meaning two of the groups are the same. Okay, and they like to ask you which ones are essential and non-essential. And they also like to ask you about cysteine that forms disulfide bonds, because this is important in the formation of a more structurally stable final protein. Okay. Last thing from at least my time that they could ask about would be the proline, because proline is the secondary amino acid. What is the third one? What are you referring to now? So we said they can ask you guys about essential, non-essential amino acids. They can ask you guys about glycine, because glycine is the only one where the R chain is the same as the hydrogen. Okay, so I'll show you a picture in the next lecture. They can ask about cysteine, because it forms disulfide bridges to stabilize the structure. They can ask about proline. The rest, if they do think to ask you guys about these, you'll know because they have an aromatic ring. But I've never seen them ask about phenylalanine versus tyrosine versus tryptophan. Can I repeat the glycine part? Okay. I'll show you guys a picture in a moment. I don't think I have one here. Okay. So what I mean by glycine, okay, is do you see how we said an amino acid has three things? Has amino group, has a carboxyl group, and has a hydrogen. And we said that always this is a chiral carbon atom or alpha carbon, because the R group is different than these. صح? However, glycine is the only exception, because this is a hydrogen and this is a hydrogen. And you'll see in the next lecture why that's important, but I'll show you that in a second. So you guys want me to repeat the cysteine? Okay. So cysteine has sulfur molecules. Think sulfur, or S is for sisters, they like to stick together. Okay, so cysteine has sulfur. They're sisters, they like to stick together and form disulfide bonds. Okay, I hope that makes it easier for you to remember. So you see the two S's here, they're sisters, they like to stick together. And when they stick together, they form this bond within the chain. Okay, these are all amino acids lined up together, forming your protein. And because they form this bond between them, it forms a bridge. And you see how it makes the protein fold instead of being straight, it kind of, okay? And the reason this is important is because it stabilizes the final protein structure. Okay, so that's why cysteine is important. Does that answer your question, Sarah? I can re-explain it again if you want me to, Adi. If it's clear. Then. Do you guys have any questions before I go to the last couple points? Okay. All good. Wonderful. Okay. Great. So now we move on to peptide bonds. Okay. We said proteins are made up of amino acids, but you need to have a way for them to stick together. They're not just going to float around and magically, magnetize. So there's a specific type of bond. There's a specific type of bond that we call a peptide bond. So peptide just means a bond between these two amino acids that helps form proteins. Okay, so this protein here attaches to this protein here. You can see how between the purple and the pink, you get a bond. This is called a peptide bond. And this attaches, and then this attaches, and then this attaches. And you can see that here, the R group, which is in green, is different. So these are all different amino acids, and they attach together by this peptide bond. And okay, cool. Now this attaches and it becomes a long chain, and then this chain folds together. Okay, and that's what forms the three-dimensional shapes of the proteins. Okay, and let's take a closer look. Okay, we said every amino acid has these different groups. Has a carboxyl group, hydrogen, amino group, and then the R groups. So like I showed you in this picture, the bond forms between the purple group and the pink group, which is the same thing here. Forms between the amino group and the carboxyl group. Okay, and so this is COOH. You lost the H, so it's negative. So it's C double bond oxygen, and there's another oxygen here. Okay, here you have nitrogen attached to 3 hydrogens. So how are we going to make sure that this bonds with this? Well, if we get rid of the oxygen and get rid of 2 of the hydrogens, we get H2O, which is water. Okay, so if we remove an oxygen from here and remove 2 of the hydrogens, now this nitrogen can bond to this carbon. Okay, and this is what forms the peptide bond. So you see how here you don't see another oxygen, you don't see another 2 hydrogens, it's just C double bond O that's bound to the N nitrogen that's bound to a hydrogen. So this bond, or this dehydration reaction, when we say dehydration reaction, we mean removing water. Okay, so when you're dehydrated, it means you didn't drink water. So same thing here, dehydration reaction, you removed water in order to allow this carbon to bond to this nitrogen. And now this forms a very strong bond, which is what allows your amino acids, all the ones we learned about, to stick together and form the single file line. Okay, is that clear to everyone? I'll just repeat it one more time to be safe. So we said this is a chain of amino acids. This is 1, 2, 3, 4. They're all different. But this end, okay, so the pink represents the amino group, and the purple represents the C double bond OH. Okay, these bind together. But how do they bind together? Here you lose an oxygen. Here you lose 2 hydrogens. So what does that mean? You're removing water, which is why we call it dehydration reaction. You're removing water. And this forms a peptide bond between 2 amino acids. Okay, makes sense? Doesn't make sense, don't worry, I'll repeat it. I just want to make sure everyone's on the same page. Inshallah, easy enough. Okay. So guys, if you're messaging me, don't message me on this. Message me on like the Maryam that's sharing the screen, I guess. So, message me here. I'll literally call myself message me here, because I can't see any on my phone. But Malaki asked, can you consider a condensation reaction? Condensation is the opposite from what I remember from chemistry, where you're, allowing water to condense into it. So I know this is a dehydration reaction because you're removing water. Yeah, I agree. If you message everyone, like, it's easier for me to see. Or just go on the message me here. Okay, so I'm assuming that everything is clear, inshallah. And now I'm gonna allow you guys to solve some MCQs. Again, I encourage you to get it wrong, because that means you're going to learn it a lot better. And don't worry, this is a safe learning environment. Heidi writes it in the chat, and we'll explain what's the answer and why. Okay, alhamdulillah. You guys are getting it. Amazing. Okay, so let's just read the question first. Don't make this mistake of not reading the question properly in your exam, because I'm very guilty of that. And a lot of my regrets in first year are because I got a question wrong because I didn't read it properly. So let's read it carefully. Which of the following statements regarding the peptide shown below is correct? Okay, so we have glycine, cysteine, glutamine, serine, aspartate, aspargine, cysteine. Peptide contains a glutamine. Actually, GLU is glutamate, not glutamine. Glutamine is GLN, not GLU. Okay. And then B is the peptide contains a side chain with a secondary amino group. Do you guys remember what the secondary amino group is? It's literally just one. But do you remember what it is? Proline. Mumtaz. Okay. And the third option is the peptide is able to form an internal disulfide bond, which you guys got correctly. Remember, disulfide bond means you have two cysteine. They're sisters. They like to stick together. So the two S's that you'll see. Okay. So this peptide is able to form an internal disulfide bond. That is correct. Glutamine is GLN. Okay, this is glutamate. Okay. So next one. Which of the following is a non-essential amino acid? Do you guys remember? Or I'll write it in the chat. The mnemonic is private Tim for essential amino acids. Okay, so now for this one, instead of saying them out loud, I'm going to take you guys back to the slide that has them all written. Okay. Private Tim Hall. We know P is for phenylalanine, V is for valine, and the two T's, threonine, tryptophan, not tyrosine. Okay. And then isoleucine, methionine. And then we have histidine, arginine, lysine, leucine. Okay. So the question was, which of the following is a non-essential amino acid? So which one is not any one of these? So now we go back to the MCQ. You guys tell me which one was not there. Aspartame, correct. Okay. Someone asked me, can methionine form a disulfide bond or only cysteine? From what I remember us learning, they mentioned cysteine is what forms a disulfide bond. But, I mean, I'll Google it for you guys now, because in theory, methionine also contains sulfur. So it could work. But I'll double check. As for now, we're finished with the first lecture. So give yourselves a pat on the back. Inshallah, this was clear for everyone. If you have any questions, please let me know. Do you guys want to take a 5-minute break? 7:57 we'll be back. Is that okay with everyone? Or okay, you know what? If you guys are tired, let's start again at 8. Does that sound okay? And inshallah, the next lecture we will finish within 1 hour. We'll start again at 8. Please, if you haven't already, go eat something, go rest a little bit, rest your brain. Thank you for answering. Made me feel like I'm not sitting alone in a room. Okay. All right. Okay, I'll give everyone like 1 moment. Okay, welcome back, you guys, to Biochem. So this is the second part of today's lecture. So first part, we talked about the amino acids, what they are, how to classify them, specific things you should know about each one. Now we're going to look more into something called the titration curve. Now, first of all, I know Dr. Abdul Jabbar Rasool is who gave you this lecture, and God bless him. He is such a sweet professor, but sometimes he can make things a little more complex and a bit more difficult to digest for a first-year student. So I hope that this lecture is given to you guys in a more, simple way and allows you to take the concepts that you learned today and, carry them through your knowledge in MOL and inshallah your knowledge in medicine, because it is something that is very essential for us to understand. God bless him for you. Okay, so again, if you have any questions, write it in the chat. Again, I say this every time, but it's genuinely something I wish someone told me in first year. Please don't be afraid to make mistakes. There is this whole, it's scientifically proven. It's called, pre-testing. So when you do questions before you even go into a lecture or start studying, and you get them wrong, your brain is wired to make sure that you don't get it wrong the next time. Or if you've ever felt that, like, I definitely have, where you make a really stupid mistake in an exam and it haunts you like till this day. You will never forget that because it was a stupid mistake. So that's the same concept. It kind of gets burned into your brain. But please don't be afraid to make mistakes, ask questions. That's what we're here for. And you guys are learning, and that's how you learn. Okay. So again, with that long-winded introduction aside, what are we going to do today? What are you guys going to learn, inshallah, by the end of this? So we're going to describe the pH scale and how a buffer regulates body pH. We're going to look back at amino acids, which is what we just learned about, right? How can they act as buffers? We're going to learn about the Henderson-Hasselbath equation, explain the relationship between pKa and pH, look at different buffers in the body inside your cells and outside your cells, and state how aberrations of pH result in acidosis and alkalosis. So if this looks daunting, don't worry. We're going to take this and break it down into smaller chunks. And inshallah, you guys are going to understand this by the end of it. Now, first of all, let's start with what we know from basic high school chemistry, acids and bases. Okay, so what are they? An acid is a molecule that can donate H+. Okay, base is a molecule that can accept H+. All right, so sources of acids in the body are mainly metabolism. So if you look at any of the pathways that they're making you learn about, you're going to see like this acid, that acid. So you can tell that a lot of these acids come from metabolism, okay? And weak acids act as buffers. And a lot of these things that come from your metabolism are weak acids. So, subhanAllah, your body is always in a balance of pH, okay? We're going to look at that in the next slide, inshallah. But I just want you guys to understand that the reason you guys are learning this, the reason it's important is because these buffer systems in the body are what help keep you alive. Because remember what we said about proteins and how they fold? If the pH is too high, they're going to denature. If the pH is too low, they're also going to break down. So subhanAllah, all the processes that happen in your body have the end goal in mind of making sure that everything is in a balance, everything is in homeostasis, okay? So again, acids donate H+, bases accept H+, okay? And the same way weak acids act as buffers, weak bases also act as buffers, and we're going to talk about this today. So now we have the pH scale. And you guys know pH runs from 0 to 14. 14 is the most basic, okay? 0 is the most acidic. And what the pH scale represents is negative log concentration of hydrogen, okay? So again, we're looking at pH as acids that can donate hydrogen, bases that can take them in instead, okay? And the optimal pH of the body is 7.35 to 7.45. And I want you guys to memorize this, not just for the exam, but because this is a concept that's going to keep coming up in medicine in the future again and again and again. These numbers are very important for you to know. So the normal balance of the human body, the balance of the pH of your blood is between 7.35 to 7.45. And I'm going to explain some of the terms I mentioned, like buffer. We're going to look at that in a lot of detail, okay? And again, just what I want you guys to understand now, we know acid gives H+, base takes H+. And our pH of the body runs right about, somewhere here, like 7.35 to 7.45. That's what is essential for you guys to know right now, and we're going to build on that knowledge slowly. All right? So we said that everything is in a balance. What I want you guys to picture for this entire lecture is a seesaw right here. So on one side, you have a weak acid. On the other side, you have its conjugate base. What does this mean? If you increase the concentration of a weak acid, it's going to decrease the amount of its conjugate base, and vice versa. If you have a lot of conjugate base, you're going to have a little bit of its acid. And I'm going to show you guys what that looks like right now. Again, I just want you to picture this in your mind. It's a seesaw. Something goes up, so something must go down. Something goes up, so something must go down. Okay, so let's say acetic acid or vinegar. Okay, for those of you who like salt and vinegar chips, like me. This weak acid, remember we said acids donate H+. So you're going to donate your H+ here. And what that's going to form is it's going to form its conjugate base. Why is it a conjugate base? Because remember, this can accept the H+ and turn back into this weak acid. So you see how it makes sense? If you have very little of this weak acid, it's because your equation is pushed this way. It's like a seesaw. If you have a lot of the conjugate base, what is it going to do? It's going to bind to all this free H+, okay? And you're going to have little concentration of your weak acid and vice versa, okay? So just to recap again, you have a weak acid. In this example, we're talking about acetic acid, okay? And it has this H group, remember? COOH. Keep in mind, this is in all of our proteins. That's going to be important in a moment. But this COOH is going to donate its H+ to form H+ and a strong base. Okay, and again, it's a seesaw. Something goes up, something must go down, and vice versa. So it's always in a balance. And I'm going to elaborate on this a bit more. Okay, so let's look at the other end. Let's look at the bases. We said bases accept H+, right? And acids donate it. So here we have ammonia NH3. Remember, this is another one of the side chains that we have in any amino acid. So this NH3, okay, or ammonia, can take in a hydrogen from water and give you OH and NH4+. And now again, the same way, if you have a weak acid, it gives you a conjugate base. Same thing other way around. If you have a weak base, it gives you its conjugate acid. So again, it's a seesaw. If you have, okay, let's say the equilibrium lies strongly to the left, which means mostly in the body, it's going to be on this side. If you have this NH3, because it's a weak base, what can it do? It's going to react with H2O, okay, to form OH and NH4, which is a strong acid. This NH4 can go the other way. It can donate its H+ to form a weak base. So you see how like the shift goes from side to side, okay? It's a seesaw, it's a buffer system. If you have a lot of the conjugate acid, what's it gonna do? It's gonna push the reaction this way. Why? Because we want to become in a balanced state. If you have a lot of the weak base, you're gonna wanna push the reaction this way and vice versa. So this is how our body maintains the pH in it. Okay, and now we're going to talk about buffer systems, okay, and what they are. But before I do that, is this clear to everyone? Revision of this basic acid-base concept? How, you know, acids work and bases work? Yes, and you can say no. No one is holding a gun to your head. Okay. All right, I'll explain again. We have acids and bases. Number one thing, acids give you H+, bases take your H+, okay? And if we're clear on that, we have different types of acids and bases, okay? So for example, this is a weak acid, acetic acid, okay? What is it gonna do? We said acids can donate H+, so the reaction goes this way. And once you remove this H+, what are you left with? CH3COO-, which is a base. Why is it a base? Because it can accept H+ and turn your reaction the other way. So again, I want you guys to think of everything as a seesaw, okay? If you have your weak acid on one side, you have your conjugate base on the other, okay? Your equilibrium, okay, or the state of balance is gonna be caused by shifts in your pH changes. For example, if you have a lot of H+ in the body, in one place, what's it gonna do? if you have a lot of H+, if you have a very acidic pH, okay, what's it going to do? It's going to bind with the strong base in order to maintain that balance. If we look at it on the other side, weak bases accept hydrogen. They take a hydrogen. So, for example, here our NH3 becomes NH4. Okay, so let's say we have a very basic environment. Okay, that means we have little H+. Which way do you think the reaction is going to shift? To the right or to the left? Good. I think we can get it wrong. Okay. Okay. So remember, it's a seesaw. If you have a lot of, let's say you have very little H+ in the blood, do you want your blood to turn more acidic or more basic? Let's put it that way. And if you have a lot of H+ in your body, do you want to form more H+, or do you want to give less H+? Okay, wait, you guys are confused. Let me rephrase it. If I give you an environment where you have a lot of acid, what's your body gonna do? Let's say here, a lot of acid. Okay, what your body's gonna do is it's going to take it in to make your pH more basic. Does that make sense? Is that clear to everyone? So if you have a lot of acid, the bases are gonna like hold on to the acid just to make sure that the pH of the body doesn't go really acidic, because that's bad for you. In the opposite way, if your body is very basic, these basically what's gonna happen is you're going to donate a lot of H+. I'll show you guys the slide so it makes more sense. You're gonna donate a lot of H+, okay, in order to make your blood more acidic. Again, it's a seesaw and your body always tries to keep itself in balance. I think you guys are gonna understand a bit more of the concept when I show you how it actually works. So I'll repeat. Okay, if we go to the basic concept of pH, pH is negative log H+, meaning if we have a very high pH, that means we have a very low H+. If we have a very acidic pH, that means we have a lot of H+. What I'm trying to say is if you have, let's say the pH of your body is very acidic, for example, what is your body gonna do? Okay, it's going to take in that H+ to make it more basic. Okay, it's gonna take in more of that H+ to help shift your pH here. It's a seesaw, it's a balance. Okay, let's say your pH is very alkaline, meaning you have very little H+ in your blood. What's your body gonna do? It's going to dissociate to give you more H+. Okay, makes sense? Because if it gives you more H+, that means your pH is gonna shift back towards being normal. Okay, so does that make sense? You can say no.
Yes.
As a basic concept, if you have a lot of H+, your body's gonna try and get rid of it. If you have very little H+, your body's gonna try and give it to you in order to maintain this equilibrium or maintain this balance. Weak acids will dissociate to give you more H+, and vice versa. Weak bases will dissociate to take in that H+. Why does it bind to a strong base? Okay, why does the H+ bind to a strong base? Why not a weak base? You mean here? It's just because of the nature of this molecule. And the way this is how acids work. Don't think of it as strong base, just think of it as a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay? I think that might make it easier for you to conceptualize. Okay, so now, this is basically what I was explaining to you guys. In order to maintain the pH in our body, we require buffer systems. So exactly what I explained to you, where if you have a lot of H+, your body is going to bind to it. If you have very little H+, your body is going to give it. That concept is called a buffer system. Okay, so what buffers are, okay, are structures, proteins in your body, okay, that minimize change in pH. They're like policemen walking around making sure that everything is okay. There's too much acid, okay, we'll control it. There's too much base, okay, we'll control it. That's how buffer solutions work, okay? They minimize the changes in pH following the addition of an acid or a base. So their goal in life is to make sure that the pH of your blood stays between 7.35 to 7.45. Okay, this is the range. So let me give you an example. Okay, just to help you guys visualize it much better. The acid, which we can see, this is the same example that I gave, just with a bit more elaboration. This is acetic acid. Remember, it's the same exact thing we saw here. Okay, this is acetic acid. Okay, so what acetic acid does, right, is that it can dissociate to give its conjugate base. Okay, and in that process, it's going to give a hydrogen. Allahumma, all we see here is that this hydrogen, this H, moves from here and then it attaches to water. Okay, and that way we form acetate. In the exact opposite way, this acetate, okay, or AC minus, can bind to H plus to form acetic acid again. Okay, so this way it acts as a buffer. There's a lot of H plus, it's gonna go here. There's a lot of OH minus, it's gonna bind and give, you see how it works? It's a cycle. So this is how the buffering system works. It's the exact same example I gave you, just with a picture. Okay, so the acidic HA, or the acid, sorry, and the base of the buffering compound can combine with any H plus you add or any OH minus. Okay, which is the same thing as lack of H plus, right? And for example, you have phosphate in your cells. If you remember that foundation lecture with, the electrolytes, what's intracellular, what's extracellular, one of the things that was high in concentration in your intracellular fluid was phosphate. And so phosphate is an important buffer inside your cells. Okay. Similarly, you have something called the carbonic acid bicarbonate system, which I'll talk about later in this lecture. And this acts as an extracellular buffer. This is the buffer in your blood, okay, because it's created from dissolved CO2. Okay, I'm gonna explain the diagram again. So what are buffer solutions? Buffer solutions is basically the seesaw that I told you about. They're gonna minimize changes in pH, because remember, that's dangerous for you, okay? Following the addition of an acid or a base. So any change in the body, okay, it's going to react quickly and it's going to make sure that this change doesn't cause a big change in the pH of your body. Okay, so again, to represent that visually, I'm going to explain it here and then explain it there again. So acetic acid, we're looking at the same thing. Remember, it's going to leave or give this H plus, and it's going to form H plus and its conjugate base. Okay, so this is the same reaction, or it can go vice versa. This conjugate base can react with H plus to give acetic acid. Okay, so let's just look at that again. Acetic acid, okay, it has H plus and AC. Okay, it's going to donate this H plus. Donate. It's gonna go here. It just happens to be bound to the water. Okay, and give you AC minus. All right. Exact same way, the other way around. Remember, it's a balance, it's a seesaw. Let's say you have a lot of H plus. What is your body gonna do? It's gonna take this acetate, this weak base, and it's gonna bind to the H plus in order to prevent this H plus from floating around in your blood and causing problems. Okay, So again, this can bind here. If you have too much OH, or your blood is very alkaline, does not have H+, what are you going to do? You're going to give it the H+. It's going to be donated, and it's going to go here for more. Let's say you have too much H+. What is it going to do? This buffer is going to take it in and give you acetic acid. Okay, makes sense? This is how the whole cycle works. This is how any buffer solution acts in the body. Okay? And then you have a value called Ka. Okay, or this is a constant value. And we're going to look at this equation in a moment. Bear with me, there's a bit of math. But most important thing, does this concept make sense to everyone? Because it's very important that you understand this now so that we can go on and build upon this knowledge. Yes, inshallah, easy. I don't get the HAT and the AC minus. HAC, okay. So HAC is just the acid. It's a, okay, let's not look at HAC, just look at this. The CH3COOH. This is the acetic acid. Okay, this is just a simplified version of it. All we're saying is, let's say there's a lot of OH minus, meaning there's a little bit of H plus in the blood. What is your body going to do? You don't want a lot of this OH minus floating around, making your blood very alkaline. It's going to give away its H, right, in order to form water. Water is neutral. Water is our favorite thing, okay? And once it donates this H, it's going to become CH3COO minus. Let's say you have another scenario. I pour a lot of acid into your blood for some reason. Your body's going to freak out, and what is it going to do? This acetate, this CH3COO minus, is going to soak up all of the, is going to bind with all of this H plus in order to prevent it from causing problems in the body by altering the pH. Does that make sense? Yes? Okay. Wonderful. Right. Now we understand this. What about H2O? Water is just floating around in your body, living its best life. The water is not our problem. Acid, base, too much of anything, and yet water, it binds to acetate and makes acid. Okay. Remember that the pH of your blood is not determined by acetic acid. Remember, what's the definition of pH? Negative log concentration of H plus. So really, your acetate is acting like a sponge for H plus, and your acetic acid is acting like a source for your H plus. You having acetic acid in your blood, by definition, does not make it acidic. The H plus in your blood that's floating around is what makes it acidic. Okay? So what if there's not enough acetate? Okay. If there's not enough acetate, then the pH of your body will be altered. But ideally, there's so many buffers in your blood that this is not a problem. Unless you get into specific scenarios, but I'm gonna give you guys clinical scenarios of that. Most important thing I want you guys to understand is this concept of giving H plus, taking H plus. All right? Okay. Inshallah, this was clear for everyone. Now, we have our pH. We all got to a point where we understand what's the pH and what is it doing. Now we have something called the Henderson-Hasselbath equation. Okay. Now we kind of look at it, and I remember looking at this for the first time. I'm like, what the hell are we talking about? Okay. Basically, we have a value called Ka. Okay. Ka takes the concentration of your H plus times the concentration of your A minus, which is your, basically that's looking at this. This is your hydrogen, and this is what your A minus is, the conjugate base, over the concentration of your, this is HA, which is basically the weak acid or acetic acid. Just stick with me, okay? So what the Henderson-Hasselbath equation says is if A minus and HA are equal, then the pH is equal to the pKa. What does this mean? If the amount of acetic acid here, okay, just stick with me. If the amount of acetic acid you have here is equal to the amount of acetate, okay, then your pH is equal to your pKa. How does this make sense? Just stick with me, okay? This is our acetic acid, this HAC. If this equals to this, then mathematically, this is going to be gone. And your Ka, or your constant for this reaction, is going to equal the concentration of your H+. I'm going to repeat it again, just please stick with me, all right? Now, the way pH is negative log of H+, pKa will be negative log of Ka. But we said that the concentration of this and this are equal. So it's like saying pKa equals negative log concentration of H+. And that's the same equation as pH. Again, all this is saying is if you have acetic acid here, concentration, equal to acetate, that means you are in balance, okay? And the concentration of H+, is what's going to determine your Ka value. So your pH is equal to your pKa. Again, so the Henderson-Hasselbath equation calculates pKa using the Ka value. This you guys unfortunately have to remember. It says that your Ka, or your dissociation constant, is equal to the concentration of H+ times your conjugate base all over the concentration of your weak acid. Okay, so in other words, okay, if you look at this equation, again, bear with me. I know we came into medicine because we didn't like math, but here we are. If all I did is I took the log of both sides, this is like saying log of H+ times log of A- over HA. All I did is I split the equation. Are A and AC the same? Yes, they're the same. It's the same. Okay, this is just referring to any acid, not just acid, or any conjugate base. Okay, all we did is we moved it to the side. Okay, log of H+ is the same thing as negative pH. Why? Because negative. What is pH? Negative log of H+. So log of H+ is negative pH. Okay. All we did in this equation is I don't want the pH to be negative. It kind of looks ugly here. So I'm just going to switch this and switch this. And if you move stuff on the other side of the equals, it becomes positive. Okay. Basically, so deriving from the Ka. Okay. Again, all we did is take log of both sides and then calculate. This equation tells us pH equals pKa plus log of conjugate base over its weak acid. If you don't want to memorize it, don't memorize it. I just want you guys to understand how we came to this conclusion. لو طار من عقلكم عادي, just understand that this is the Henderson-Hasselbath equation. Okay? And the reason it's important is because once we reach that equilibrium point where the pH, okay, and the pKa are equal, because these two are the same, then a system has its most buffering capacity. It's very strongly able to deal with any change in its pH. Okay. I'll one last time because I know it's very confusing. You have acetic acid, for example, okay, and acetate. We went through the whole concept of it donates H+, it takes in H+, etc. this equation has a constant, okay, or your Ka. Ka says concentration of H plus times acetate over concentration of acetic acid. Hello? Doesn't have to be acetate, can be any weak acid you have. Hello? It tells you that pKa can be calculated. So your pH equals your pKa plus log of your conjugate base over your weak acid. Why do we care about this? If acetate, for example, and acetic acid are in equal concentration, if they're in balance, يعني مثلا لو قلت لكم 2 divided by 2 is what? 1. Okay? Log of 1 is what? 0. So at this point where these two values are equal, your pH equals your pKa. Okay? If you don't remember anything, all I want you to know is when the values are equal, a system has its most buffering capacity because your pH equals your pKa. All right? You don't need to memorize all the steps. I just included it so you guys can understand and what's going on and not just like be thrown. Like I would hate it when they just throw math at me and I don't know what it means. But I'd always take the time in the end and understand what's going on. Okay. I'm gonna explain what that means in a second, just as for a moment. Okay. We've been talking this whole time about buffer this, buffer that. طيب, how does the buffer actually work? Okay. The A is the acid, it's the same as this. AC and HAC. Just ignore the C. It's just the same concept. Weak acid, conjugate base. Yes. This is just so you can apply it to anything, not just acetate. Yes, you're right. Okay. So let's recap what we said about buffers. I told you that the normal pH of the human body is between 7.35 and 7.45. We can all agree on that. صح? So the buffer systems in your body are going to do their best to always keep your pH between these two. Because if suddenly your pH changes in your nucleus, all your DNA is damaged, your cell dies. You can't do anything about it. Okay? Let's say pH changes in your blood. Suddenly, all of the cells in your blood, go haywire. There's damage all over the body, in your kidneys, in your red blood cells, everything's out of whack. We do not want that, definitely. And changes in pH would change the function of enzymes all over your body. Basically, nothing is working properly if your pH is not between 7.35 and 7.45. Okay? So, with that being said, let's look at pH of acetic acid buffer versus HCl. Okay? What I want you guys to look at is, you see this graph? Basically, what this is telling you is, I keep adding acid. Okay? But ignore all of the numbers. All I want you to see, okay, is here, you added an acid to 0.1 molars of a buffer. Do you see how much it changed? Like how quickly it changed? But here you added an acid to 0.2 molars of a buffer. You have more buffer here. You see how like the change is much less? So that's the same concept. The more buffer you have in your body, the more buffer you have in your blood, the more able you are to deal with these changes in pH. That's why it's important. That's why you guys are learning this math and learning this lecture and caring about it. Again, I don't want you guys, it's a Maryam graph. All I want you guys to understand is the more buffer we have, the better you are able to handle these changes in pH. Is that clear? Just that basic concept, why pH and buffers are important. Yes? Okay, wonderful. Now, I just spent the better part of 37 minutes talking to you guys about all of these different things. Okay. A buffer is something that prevents a change in its pH. Yeah. A buffer, like the example we kept using here, or you know what, I'll use this example. It's easier for you guys to visualize. A buffer is anything that can take, here you have a lot of H+. It's going to suck it up like a sponge, okay, in order to prevent you from having changes in your pH. That's what a buffer is, okay? And vice versa. Hello? You have a lot of OH minus, it's going to give you H plus in order to prevent you from having a lot of alkalinity or acidity. Okay? So now that we're clear on that, again, I've been talking about buffers and pH and math and all these annoying things. Why do we care? What does this have to do with amino acids? Well, remember what I told you. Amino acids have 4 groups. You have your basic group, you have your acidic group, you have your H, and then you have your side chain. So if you look at it automatically, remember the equations I gave you in the beginning? One of the examples was ammonia, صح? Your other example was acetic acid, which had at the end of it COOH, right? So this can act as a buffer, صح? This can give you H+, okay? This can accept H+, okay? So the amino acids that we're learning about, by nature, can act as buffers. Why? Let's say you have a very, acidic environment, okay? And the end of this is COO minus. What can it do? It can take the H+, right? You can put the H+ on the amino group in order to prevent your body from having a lot of H+, a lot of acidity. Same way the other way around. Let's say you have a lot of OH minus. What can it do? It can donate the H+. Okay, so you see how it can work as an acid and a base. Okay, and again, all amino acids have minimum 2 because they always have an amino group and they always have a carboxyl group. However, some of them might have a basic side chain, remember, like histidine. Some of them might have an acidic side chain, like glutamic acid. Okay. So, like I said, we have acidic and basic amino acids. Remember the slide I told you about in the So, because of that, some have more acidic capacity, and they're better able to handle. They can donate more H+. Other ones are basic, they can accept more H+. Okay. So this is just, again, to recap what I said. All amino acids can be buffers. Why? Because they all have a carboxyl group or COOH, and they all have an amino group or NH2 that can act as weak acids or weak bases. Okay, so if the amino acid has 2 ionizable groups, it has 2 pKa values, and 3 groups has 3 pKa values. Relax, I'm going to show you what this means in a second. Okay. We're going to talk about something called the titration curve, which is what we've been leading up to for this entire lecture. Now, what I want you to know, sorry, where does leucine fit? What makes the acidic and basic amino acids different from the rest? It's the side chain. The side chain is acidic or the side chain is basic. That's what changes. Okay. Now, rules to remember. And if you guys remember anything, remember this. If pH equals pKa, remember the amount of your conjugate base is equal to the amount of your weak acid. I mean, they can be better buffers, but it depends on the environment they're in. You'll understand this when I talk about the curve a bit more. Okay. But if pH equals pKa, then these two concentrations are equal. Remember how I told you it's the middle value. If these two are equal in the whole cycle that I kept talking about, your pH is equal to your pKa. Okay. If your pH is higher than your pKa, okay, remember high pH means we're in a basic environment. That means you get more A minus. Now again, let's think of this as a seesaw. Okay. If your pH is high, okay, your weak acid is going to do what? It's going to donate H plus. صح? Because if you have a very alkaline environment, what do you have in the blood? A lot of OH minus, very little H plus. So in order to create this balance, what is it going to do? It's going to give you a lot of H plus until you reach this seesaw balance equilibrium. Okay, let's say your pH is very acidic. If you have a lot of acid, what's it going to do? It's going to bind with the conjugate base. You have a lot of conjugate base, and it's going to seesaw back in the other way. Okay, and I'm going to show you guys this on the graph again, just to make sure you understand it. So we said this is the point where the pH equals the pKa. And we talked about something called buffer capacity. Okay, and what that means is, do you see this blue zone? This blue zone is not on the third floor, but instead tells you how much buffering this can do. Because you get to a point where, like I showed you in this graph, you keep adding acid until خلاص, you can't. There's no more buffer left for you to fix the pH. Like everything is gone. So it's the same thing here. This blue zone is where you have enough buffers in order to balance the pH. If you have way too much OH minus or way too much H plus, خلاص, you can't buffer anymore because there's not enough left for you to give or take. Okay, so again, I'm going to repeat this. We know the three rules. If pH equals pKa, that means the concentration of the weak acid and the conjugate base are the same. Okay, this is the whole mathematical thing I tried to prove to you guys. If pH is greater than pKa, okay, which if the pH is higher, see how there's a scale, okay, that means you have more of what? Your weak acid or your conjugate base. Let's think about it. If the pH is high, that means we have a lot of OH minus. Do we want to give H plus or do we want to take more of it? Just tell me, give or take. Okay, let's go through it again. If we have a lot of, if we have a very, okay, let's start with the acid. Acid is easier. If we have a very acidic environment, okay, meaning pH is lower than the pKa, this middle point here. If the pH is very low, lower than the pKa, then your body is gonna wanna take that H plus. If your pH is low, that means you have a lot of H plus, so you just wanna suck it up like a sponge, take it. Okay, why? So that it doesn't mess up your pH. Okay, so what we're saying here is, if your pH is lower than your pKa in this zone here, if it's lower than your pKa, then maybe it's easier if you guys look at here. Sorry. At this point, your CH3COOH is equal to your CH3COO minus. This is your middle point. So this is what we kept talking about. If I add a lot of acid, I add a lot of H plus, what's gonna happen? This CH3COO minus is gonna act like a sponge. It's gonna take in all that H plus. So when you look at this point of the curve, you get more CH3COOH. Why? Because it's taking in all that H plus. Again, why? Because we're trying to make sure the pH doesn't change. Okay, does this part make sense to everyone?
Yes, thank you.
Yes? Okay, great. I'll repeat it again. This point, We said they're equal. This is the rule. They're equal because the pH equals the pKa. Hello? Okay. Now, what if I told you, let's see if I can write. Okay. What if I told you I added a lot of H+? What is it gonna do? It's gonna bind to this, sorry. And here the pH is decreasing. pH is going down. If pH goes down, that means H+ is going up. Sorry. So the further down you go, the less you go from the the lower the pH is than the pKa. What you're doing is you're just binding all of this H+. So if you bind all of this H+, what happens? The CH3COO minus turns into what? CH3COOH. So all we're saying is at this point, when you go lower, okay, you have, here, if you go lower, you have more HA, meaning you have more of this, where the H is bound to your acid, okay? This is your weak acid. Hello? Stay with me, let's look at it from the other side. If your pH is much higher, meaning you have, if your pH is much higher, meaning you have a lot of OH minus, this way. What are you gonna do? Does it make sense that this is gonna keep taking H+? No, you want H+, صح? You're gonna donate this H to go bind with your OH. Does that make sense? If this H goes and binds here, that means what? You're gonna create more CH3COO minus. Wait, I'm gonna clear the board so you can let's see what I mean on either side. Okay. So what I'm saying is, if you have a lot of OH minus, your body's gonna do what? Give H+. Where is it getting the H+ from? From this. Okay. Hello. If you have an alkaline pH, that means you have a lot of OH minus and very little H+. So if you have little H+, it doesn't make sense that your body's gonna go take it. And that's not enough. There's nothing. So what is it gonna do? This is gonna act as a weak acid and donate H+ and form its conjugate base. Okay, so the more the pH is than the pKa, this is your pKa point. Okay, the higher the pH, the more you get this CH3COO minus. ليش? Why? Because you have more OH. So remember, it's a seesaw. So your body decides, okay, I want to form this. I want to give you my H+. What's left? CH3COO minus. What if you go in the other way? Again, I'm just going to repeat. If you have a lot of H+, now your body can work to soak it up. So this CH3COO minus can bind to your H+ and form more CH3COOH. So if you go down, you're gonna have more protonated. If you go up, it's gonna be less protonated, meaning you have A minus. Why don't strong acids donate H+? Because in chemistry, they hold on to the H+ more strongly than it's able to dissociate from it. It's just the general rule in basic chemistry where weak acids are what donate, which is why we have weak acids in the blood, not strong acids. It's just how it works. But again, does this make sense? If I add a lot of H+, your body's going to soak it up. This is the same example I keep giving you, okay? If you have a lot of H+, your body's going to soak it up, okay? If you have very little H+ or a lot of OH minus, your body's going to give H+. Okay? is a buffering region specific for certain amino acids. Okay, so Sam, you're gonna see in the next slide that this is the buffering region for this amino acid, the specific amino acid. Okay, and different amino acids have different buffering regions. Remember how I said, if you have an amino acid that has a basic group, it's gonna have one extra buffering region because it has one extra pKa, and you'll see that in a second. It depends here, it changes. So I'm gonna repeat this concept again on the next slide just because I don't want to take too much of your guys' time. Okay. Oh, laser pointer. Wow. Sorry. Okay. So let's look at glycine. Glycine, remember, I told you it has two, okay, it's the only amino acid that has two hydrogens attached to it. Okay. Non-polar amino acids will only have two pKa values like this. Also, they probably won't, they'll probably ask about glycine, but just stick with me and you're going to understand the concept. So this is your amino acid, صح? Your carbon with two hydrogens, so this is glycine. And glycine has what? An NH3 and a COOH. So the COOH has its pKa value, okay? And the NH4 has its pKa value. So it's like pKa1 and pKa2. Why? Because this is acidic, this is basic. That's the only reason. Okay. And if you take the midway point between the two of them, this is called the isoelectric point. What this means is here, this molecule has a neutral charge. Okay, يعني on one side it's negative, on one side it's positive. Okay. So this is just isoelectric, meaning iso, same, electric, charge. Okay, they have the same charge. So now with glycine as an amino acid, how does it work? If I add acid, okay, your COO minus is gonna accept it. صح? That's the whole point of COO minus. It's gonna accept it and it's gonna go this way. Remember, it's a seesaw. Again. Let's say you go the other way. I add base. If you add base, what do you want to do? You want to donate H+. So here, this NH3 is going to donate an H+. Makes sense. Okay, it's the exact same example that I showed you guys. It's just 2 instead of 1. Okay, so I'm just going to read this, but it's exactly what I just said. Upon titration with an acid, okay, it accepts H+ and thus acts as a base. Okay. Gain of H+ means the molecule is positively charged when pH is less than Pi. So if I give you H+, it means this molecule is going to be positively charged. What am I talking about? Just look at it here. If I give H+, what's going to happen? It's going to accept it here, right? And then it's going to become positively charged. You see how there's NH3+? What if I go the other side? It's the exact opposite. Upon titration with a base, this is going to donate H+. If it donates H+, what happened? It lost the positive charge. Now it's just COO minus. But this is negative. Okay. The reason it has 2 pKa's is because the NH3 group has its own pKa and the COOH has its own pKa. So that's why I'm telling you guys, if you have 3 groups, let's say NH3, COOH, and then another COOH, this molecule is going to have 3 pKa's, and vice versa. It's just how many groups can act as buffers.
Can you please repeat this slide?
I'll repeat this whole slide. Now, most important thing is that you guys understand. Let me clear the erase all. Is that you guys understand how this works. If I give you a lot of acid, what's gonna happen? The conjugate base is gonna bind to it, صح? Until you get equilibrium. If I give you a lot of base, The weak acid is going to release a lot of H plus in order to create its conjugate base. Okay, it's a balance. And so if this is one molecule that has one side chain, so every side chain that you have has its own pKa value. This is one side chain, so it's carbon, hydrogen, 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 and then one COOH. When we look at amino acids have minimum two side chains. So they always have NH3. They always have COOH. This is like the basic principle we established in the last lecture. So because you have a COOH, you have its pKa. And because you have an NH3, you have its pKa. That's why we have two. Okay? And what we're seeing here is, now, if you look here in the middle, if you have +1 charge and -1 charge, it balances, becomes zero. It becomes neutral, which is this middle point here. Okay? If I add a lot, it's neutral, I add H+, what's going to happen? This negative charge is going to accept it. And so this whole molecule has a positive charge. Why? Because now it's NH3+, you lost the negative. But let's say I add a base. Let's say I add OH-. What happens? The NH3 is going to donate its H+ in order to neutralize it. Okay, and now this is going to have a -1 charge. So when we say you have an isoelectric point, remember, iso means same, electric is charge. It's the point where the charge of this molecule is zero, meaning this is positive, this is negative. Okay, again, these have different buffering regions, which is it's literally, it's this exact same picture, just instead of this, you just have an extra one. It's just an elongated curve. Okay? You guys understand the concept? Oh, okay. I'm sure you understand the concept of how it accepts or donates H+. Are we all clear on that? Yes, please. And we understand that an amino acid always has two groups. So always has NH3, always has COOH. Because it always has these two, NH3 has its pKa, COOH has its pKa. Okay? So depending on whether the environment is acidic or basic, these groups can react to either donate hydrogen or accept hydrogen. Okay? Now, again, I know it looks complicated, but just bear with me. Now it's the exact same thing that we just said. But instead of two groups, you have an extra one. Remember the buffers I told you about, the ones that were acidic or basic, histidine is basic, arginine is basic, all of these. If you have an extra group, what does that mean? You're just going to have one extra curve, one extra bump on the curve. Okay, one extra pKa value. So in acidic and basic amino acids, these amino acids have three ionizable groups, which is what we were talking about, like the NH3, the COOH, that's just what an ionizable group is. Okay, and these three ionizable groups can act as buffers. So they have NH3, they have COOH, and then they have their side chain. What does this mean? This means that they will have three pKa values because they have three ionizable groups, and thus three buffering regions on the graph. So you see how you have like one dip, second dip, third dip? They're just the different pKa values. Okay? Again, it's literally the exact same thing I just said here. Allahumma, instead of two, we just have an extra one. Okay? And remember, the isoelectric point is always the point in the middle, the point where both charges are equal. The charge is zero, it's isoelectric. Everything is constant. Okay? So the isoelectric point is where pH equals pKa. So just the middle point, the balance point. Again, just to compare. Here, this would have been our isoelectric point. well, it wouldn't really have made a difference because they're equal, صح? But if we look here in the next slide, the isoelectric point is in the middle. At this point, the pH equals the pKa. If you look at it here, it's the same. It's always in the middle. Okay, it's just called this time pKr because there's an extra group. pKr referring to like the R is the side chain. But it's all the same. You see how it's always, neutral in the middle, neutral in the middle, neutral in the middle. It's all the same. Okay. Sometimes for specific groups, it might be neutral. The curve might look weird. So it's neutral here again at pKr. This is just glutamate. And you can see the pictures with like net charge here. It's +2, here it's +1, here it's 0. I don't want you guys to get into the details. I just want you to understand how we got to this point. Is that clear? Here we have 3 pKa values. Why? Because we have an R group that can also act as a buffer. Okay. Let me go back to like. خلاص? Clear for everyone? Any questions? Okay.
الجلوتاميت ليش مو بالنص؟
تعيدي لي السؤال؟
الجلوتاميت ليش مو بالنص؟
Because that's just the way the molecule works. Like I didn't put it there, but it's just كده. It's just the R group works in this way.
طيب هل يعني هو الوحيد اللي ما يكون بالنص؟
هو شوفي مني لا تركزي عليه. It doesn't really matter. What's more important is that you understand the concept of the pKa values. I think هو مو الوحيد, but يعني I didn't sit and look at all of the graphs, like these are only the relevant ones that they gave you. عرفتي؟ وأهم شيء is that is pKr is the isoelectric point when ما كان. And it's usually in the middle. It's the point of balance. So it's كده في النص. And at this point, your pH is equal to your pKa. Everything is the same. Okay? And it's the same as this one. هنا قلنا pH is pKa, صح؟ هنا قلنا Pi equals pH equals pKa. It's the same thing. هنا pH equals pKa equals pKr. يعني كلها it's the same. عرفتي? It just depends on like the middle value. Okay. فالحين I know that it's 9 now. I'm gonna try and finish up as soon as possible. But again, if you guys understand the basic concepts, then everything else is gonna be much easier. Now let's go back to homeostasis. Again, I spent an hour explaining this and the buffer and how this works and blah, blah, blah. Why do we care? Why does it matter? So homeostasis is a state in which our body is in balance. Okay. And so buffer systems require a pKa that is near the pKa of the human body. Like if you look here, and I told you the pKa here is, okay, let's take this example. It only buffers between 3.76 and 5.76. The pH of my blood is 7.35 to 7.45. So why would I use this acid in my blood? It does not make sense. صح? We want something that's gonna buffer at a point where our body's pH is, because that's what matters. So for example, you have 2 main buffers. You have intracellular buffers, phosphate and histidine. And histidine is the most important intracellular buffer. And extracellular is your bicarbonate carbonic acid system, which we're going to talk about now in detail. Okay? But again, we understand what are buffers, how do they work, why are they important, and now because we know what the pKa is, it only makes sense that it has to be in a region where the buffer will work in our body, in our blood, and inside our cells. Okay? Now, intracellular buffers, like the phosphate buffer, okay? So phosphate is abundant inside our cells. We have a lot of phosphate. And why do we use it as an intracellular buffer? Okay, because the physiologic pH okay, inside our cells, which, let me show it to you guys on the graph. So the pK value, okay, lies near this pH value, pK2, which is 7.2. So this, you see how like this region will be the buffering region, you know, تقريبا. So it's going to work as a buffer at the pH of our body inside our cells. So gets a gold star, it'll work. That's what matters. Okay. So intracellular pH is a bit more acidic than the pH in the blood. So 6.9 to 7.4. But again, most important thing, and subhanAllah, why do we have phosphate inside the cells? To act as a buffer and to be used as like ATP or it acts as a buffer. So why do we have this that acts as a buffer? Why do we care about this? Because its pK2 value here, or pKa value of one of the side groups, works as a buffer in the cells at this specific pH. Okay, same concept. Let's look at the carbonic acid buffer. احنا قلنا right here, intracellular buffer, phosphate and histidine, extracellular buffer, bicarbonate and carbonic acid. So we talked about phosphate. Now let's talk about carbonic acid. So carbonic acid, how does it form? أولاً, we all know that we breathe in oxygen and we breathe out CO2. But there's always a level of CO2 that's in your blood, and you're not only breathing oxygen. Why? Because of metabolism and all these things. So what happens is, let me just move the chat. So what happens is you have this carbonic acid, HCO3. Okay, so it's basically formed by your hydrogen and your carbon and your oxygen. So think of it as CO2 plus H2O is going to give you H2CO3. Now, H2CO3 is our weak acid. Remember, it's like all of the pictures we've been looking at. They're all the same. They all work the same way. This is going to dissociate to give you H plus and HCO3 minus. Okay, now, this makes sense. Why does this make sense? First of all, let's say you have a lot of acid in your blood. What's going to happen if you have a lot of acid in your blood? This HCO3 is going to suck it up and then turn into H2CO3, and then you're going to breathe it out as carbon dioxide. Okay? Now, also works the other way around. Okay? Let's say you have a lot of alkalinity, okay? You have a lot of OH. What's going to happen? This H2CO3 is going to give you more H plus so that we can deal with that. Okay? And how does this relate to breathing, and why do we have a picture of the lungs and the kidneys, and why does that even make sense? So let's say you have a lot of acid in your blood. Let's take the same example we were looking at. Just bear with me, okay? You have a lot of H plus. You have a lot of H plus. Basic principles we talked about. It's going to bind to HCO3 minus and form H2CO3. Okay? And then it's going to be exhaled as carbon dioxide. But when your blood is acidic, you're going to want to exhale more carbon dioxide. So you're going to see the patient breathing very rapidly. Okay? They're going to hyperventilate. Okay? What if it's the other way around? What if it's very alkaline? Okay, your body can do the opposite. It can hypoventilate, meaning you're breathing less. Okay, so faster breathing is you want to get rid of more carbon dioxide in the blood. Okay, slower breathing is your blood is more alkalotic, not acidotic. So you have less acid in your blood, or it's more alkaline. Okay, so let me repeat this again, just from scratch. We know the rule I told you guys to remember for the rest of medicine. Normal pH of your blood is 7.35 to 7.45. Okay, and you know that we eliminate carbon dioxide through the lungs. Okay, you inhale oxygen and you exhale carbon dioxide. Okay, and the pH of your blood is maintained by a buffer system that has carbonic acid. Okay, and the way you balance it is by controlling your breathing. So again, if you have a lot of acid in your blood, what happens? it binds to HCO3 minus, becomes H2CO3, and now here. It gets released as carbon dioxide. So if you have a lot of acid, that means you're going to push this side. You're going to make a lot more carbon dioxide. And your brain is smart. It's going to realize that there's a lot of carbon dioxide. So what is your body going to do? Get rid of it. Breathe as fast, not as fast as you can, because you're going to increase your respiratory rate. Okay? And it works the exact opposite way. If your blood is very alkaline, not acidic, you're going to breathe slower. Why? If it's alkaline, the reaction is pushing this way instead of this way. Again, think of it as a seesaw. If you have a lot of acid, your body's going to push this way, make more carbon dioxide. Your lungs are going to say, okay, let's breathe it out. If it's very alkaline, your body's going to push this way and it's going to say, okay, let's slow down our breathing. Does that make sense? I know it's been a long lecture and I grilled your brains, but do you guys understand how, does the seesaw make sense? I hope, because that's how I understood it, first year and beyond. Okay, wonderful. Now, of course, I'm going to send you guys the whole PowerPoint, all the questions are there, don't worry. And it's also in my Google Drive that I sent you guys. I'll resend it anyway. But now, we just talked about, if there's a lot of acid in the blood, how your body reacts. Why is this important? Okay. Just to answer your question, kidneys can help create bicarbonate. So it helps replenish bicarbonate when it's low, which can help the system from, with moving forward. And you remember when you guys asked before, what if you don't have enough buffers? Again, subhanAllah, the way the human body is made, it's in a way that it always makes sure that we have ways to replenish. So that's just what the kidney was saying. Does that answer your question? Okay, great. So now, again, why is this important? If a person is hyperventilating, they're breathing very heavily and very quickly, exactly what I said, you're getting rid of the CO2. Okay? If you're getting rid of the CO2, you're losing that carbon. Right? So you have a lot of acid in the blood, you're breathing out very quickly, so you're losing that acid, and if you lose acid, you become alkaline. Makes sense, huh? Okay. So in this case, what we call this is respiratory, because we're breathing, alkalosis, because we make it more alkaline. Okay? So if a person is hyperventilating, losing a lot of CO2, losing a lot of acid, we call this respiratory alkalosis. Okay, and I realized there is a mistake. Oops, sorry guys. My bad. I just wanted to fix a typo. My bad. Sorry. Okay, we're back. Like, in the same way, if a person is hypoventilating, breathing too slowly, less CO2 is eliminated than normal. When you eliminate less CO2 than normal, it's the exact opposite. So more CO2 is there. So you get more carbonic acid, so the blood becomes more acidic. Okay, so that's basically saying here, if you're breathing very slowly, what happens? You have more CO2 that makes more carbonic acid that dissociates to give you more H+. So now you have more acidic blood. Okay, and so it's the exact opposite. That's why we call it respiratory acidosis. Okay. Does this make sense to everyone? Again, it's the same thing I explained in the previous slide, just with a okay. So this is, if you guys saw the picture here. So let's say, again, whatever we learn, I want to make sure you guys understand. Can you see the screen? I mean, I can see it on my phone. So I hope you can see the screen.
Yeah, we can.
Okay, so again, other than having your blood acidic or basic, let's say, someone has pulmonary obstruction. which means there is a problem with the lungs where you cannot exhale enough. If you cannot exhale enough, you can't get rid of the CO2. What happens? CO2 builds up, becomes carbonic acid, leads to more acid, right? So these people can have respiratory acidosis because it's like they're hypoventilating. Let's say there's a tumor, let's say they have an asthma or something like a problem. You can't get rid of the CO2. So because you can't get rid of the CO2, it builds up, you have more acid, and we call that respiratory acidosis. Okay. Now, do you guys have any questions before I ask you questions? Well, are we all good so far? And I know it was a dense lecture, but inshallah, the concepts are as clear as possible. All good? Okay. Now, the pH of body fluids is stabilized by buffer systems. Which of the following is the most effective buffer system at physiological pH? Now, I wish بس يعني افتح slides حق الدكتور هناء ودكتور عبد الجبار because I don't want to be liable, but the concepts are mostly the same. So last thing, I'll just re-explain the last slide. Actually, you guys know it. Okay. At physiologic pH, which is 7.35 to 7.45. Remember, this is your physiologic pH. Okay. You have a balance between your acid and your base, like everything we're talking about. So, like I explained before, if you have a lot of H+, what's going to happen? HCO3 is going to bind to it, it's going to push the reaction this way. And when you have a lot of CO2, your brain is smart. It's going to realize there's a lot of CO2 and you're going to start to exhale more. You're going to start to breathe faster. You're going to start to increase your respiratory rate. These all mean the same thing. And what that means is this patient is hyperventilating, okay? You're breathing faster than normal. And when you hyperventilate, what are you doing? The whole point was that we're losing acid, right? We're making it more alkaline, okay? Which is why we call this respiratory alkalosis. Let's say the opposite scenario. Let's say your pH is you have a lot of OH minus, okay? It's very basic, okay? Your body is going to go in the opposite way. It's going to want to make more H plus in order to balance it off, okay? And in that case, you can decrease your respiratory rate. You can breathe more slowly, okay? You can hypoventilate. So if a person is hypoventilating or breathing too slowly, that leads to an accumulation of acid, right? You get more acid because the reaction is pushing this way. And that's called respiratory acidosis. Now, the way this is clinically relevant is, let's say there's a part of your lung that's stopped, it's obstructed. You cannot get rid of the CO2. If you can't get rid of the CO2, you get more carbonic acid, you get respiratory acidosis. So people with obstruction in their lungs, like something that's blocking their lungs, blocking you from being able to breathe out properly, can cause your pH to drop, okay, which causes your respiratory acidosis. That's just the concept that's listed here. Okay. Does that explain your question? Does that answer your question? That's the best way to say it. Oops. Okay. Like, wait, guys, wait. هد شوي. دقيقة. Wait. Before you answer the question, let's read it. Okay. The pH of body fluids is stabilized by buffer systems. So we're now talking about the extracellular space. Okay. Which of the following compounds is the most effective buffer system at physiologic pH? Remember, I'm not going to tell you what it is, but remember, what is physiologic pH? What does that mean? It's a bit of a tricky question, but the concept is important. And they get it wrong, guys. Well, they get it wrong. It's okay. There are absolutely no consequences. Okay. Now, the question is, let me just ask you first. What is physiologic pH? Anyone write it in the chat. The number that I told you to memorize until the end of your medical career. Mumtaz. Okay, excellent. And when we talk about physiologic pH, we're talking about the pH in the blood. صح? And it's another way of asking, what is the best buffer system in the blood? So the answer is bicarbonate. Okay, makes sense? If I was asking you, what is one of the best buffer systems in intracellularly, you could tell me phosphate or histidine. Okay, but mostly histidine, but phosphate is another option. Okay, all of the above doesn't make sense because protein buffers differs from like where they're in. Intracellular is different than extracellular. But the key thing is that when we're talking about physiologic pH, it's 7.35 to 7.45. And at this pH, the most important buffer system, like I told you guys here, is your carbonic acid buffer, okay, or your bicarbonate buffer. Make sense? I'm so sorry, guys. It's been a long day, I think, for all this. Okay. So inshallah, that was all good. Now, next question. The greatest buffering capacity at physiologic pH would be provided by protein rich in which of the following amino acids? You guys got it. Now, let's explain this in a way that will make you, I just want to make sure that you guys understand this concept. Now, when we say the pH, I'm sure I can write this without looking here. We said 7 point, please ignore my handwriting, I'm writing with a mouse. So you're anyway, 2, 7.45. Now, in pH, anything greater than 7 is what? I'm so sorry for my handwriting. Is a base, right? Anything less than 7, I'm just going to write A instead of acid, is what? An acid. Let's ask this question in another way. Which of the following has a basic side chain? Or remember, like we had histidine, arginine, so of all of them, histidine is the most. Whatever. Histidine is the most basic. Okay. However, remember I told you. Just go back to the slides. Remember I told you here. The very important intracellular buffers are phosphate and histidine. Okay. So by proxy, although like the other ones can act as buffers, the most important physiologic buffer in protein wise is going to be histidine. Okay, is that clear for everyone? So, and I'm going to clear this because I heated 100. Okay, I know it was a long lecture, and I hope that you guys retained something. But I know I struggled with this a lot, especially in first year for any. If you're still confused, this video is very helpful. This guy, his name is AK Lectures. You might have come across him. He's very, very helpful. AK Lectures, Command and Engineered Science. They are really great at explaining, especially MOL concepts. But yeah, I think we should be done. If you guys have any questions, please email me. Okay. I just want to show you guys one last thing before we go, because I know it can be very helpful for you guys. if you can keep the recording on for this part, that would be much appreciated. Like, yeah, Google Chrome. Okay, so I want to make sure you guys know about two things. One is the resources Google Drive. Okay, and in the resources Google Drive, you guys basically have everything. You have all videos, and you can, osmosis videos are very helpful for first year. Few videos for biochem, if you're really confused about anything, it's very helpful. We also have all textbooks and include biochem module with like question banks and everything. That's one resource that I just want to make sure that you guys know about in case we sent it and you ignored the message, which is very valid because I ignored like 90% of my messages in first year. What happened? Okay. What happened? Oh, my bad. Sorry. Anyway, second thing is there is a Google Drive that I shared with you guys, and I'll share it with you again. But just what I wanted to emphasize for you guys here is one, you have this PDF which has all of your resources, and كل resources and كل like Dropbox links and OneDrive. If you click on this, this is the one that I just showed you, but you just have to log in with your FSLE. Second thing, my notes for first year are all here. Also the pre-med 2020 drive that has a lot of lectures that can be helpful for you guys. And lastly, I think it's in MOL, yeah. All of like the PAL sessions I gave, and amino acid synthesis, degradation. This lecture I just gave you, carbohydrates, glycolysis, urea cycle. Like these are all the sessions I've given over like the course of my 5 years. There's also this link that has first year resources from my colleague Iman Chaudhry. Kind of just like gave you guys a little note. We made this last year. Again, it has just a compilation of very helpful resources that can benefit you guys, and links to them, and specific things for physiology, histology, biochem, everything. But and I just wanted to let you guys know specifically right now because it's difficult to convey it via message always. Yeah, I hope this helps. I'm gonna make sure you guys get the links and the presentations, but I'll send them as the Google Drive link for you guys to go to, and the resources and everything's there. Thank you guys for attending. Big heart to you all.
Thank you so much, Maryam.
You're welcome. Allah يوفقكم إن شاء الله. Like the MOL exam is the best thing you've ever taken. وإن شاء الله سهلات وموية. And this is, I didn't introduce him, wait. This is Gary, my skeleton. He's been with me in like first year. He got me through MOL. So like, inshallah he'll get you through MOL too. 1 and 2. So yeah, guys. I'm sorry it took so